going to turn on the recording now. Okay,
Yeah.
so thank you to everybody for coming, and I just turned on the recording. So if you wrote your name earlier, it won't get recorded. So even if you wrote your name earlier, please write it one more time into the chat, so that we can get it. Yeah, only names that are written after the recording starts get preserved. Okay, so yeah, I hope everybody's had a good week and is ready to do some differential calculus today. So we'll start as usual by going over the homework. And I know a lot of people had a bad network last week, so I want to make sure that we do enough review so that what we do today isn't confusing to everybody. So I want to recall, a couple of the big ideas that we talked about last week and then go over the homework. And then I want to go very slowly today to do something that several people who handed me their homework assignments have already done, which is this power rule for differentiation that we didn't really talk about. So we're going to talk about this today in a lot of detail. But before we get to that, I just want to make sure that we have a nice review of everything. So again, thank you for coming as always, and I hope everybody's doing fine, is in good health. Um, and yeah, so let's go start off, and more people will come in as they come in. So I want to start by just reviewing what are these two major ideas that we talked about yesterday. So the first major idea was we talked about how to find the slope, no, the slope of the tangent line to a graph, right? We talked about what the slope of a tangent line, what a tangent line means, and we talked about this procedure of using a limit in order to find the slope. So what we did last time was we said that if you have the graph of a function, y equals f of x, and if you take some point on the graph of that function, so we call that point AB, then the slope of the tangent line to that point, how do we figure out the slope? Well, we had to take a particular limit. We had to take the limit as x approaches a of f of x minus f of a over x minus a. And what this ratio was actually the slope of a secant line, right? Remember, that's a line that goes through 2 points of the curve, and we're taking the limit as those 2 points get closer and closer together. That's what this limit means. And then we also showed last time that we can make a little change of variables. If you take a new letter h and you call h to be x minus a, then this limit up here is the same as this limit down here, which is used a little bit more often. So we can rewrite this as the limit as h approaches 0 of f of a plus h minus f of a divided by h. And now remember, like, what happens if you just punch in h equals 0 here, then what you're getting is f of a plus 0 minus f of a over 0, which is, f of a minus f of a over 0, which is 0 over 0, and this is indeterminate. Which means that in order to evaluate this limit, you're never going to be able to just punch in h equals 0, right? You're going to need to do something with the limit to evaluate it. And we've seen a lot of the things that you can do. A lot of times it involves some simplification or some canceling. You've got to do something with the expression before you can actually evaluate the limit. Okay, so this is what we did. We had this formula to find the slope of the tangent line, and then once you find the slope of the tangent line, it's not so hard to find the actual tangent line because you know a point on it already, because you know it goes through the point AB. So we'll see this on the homework. We'll do a review, some practice with finding this. But first, I just want to recall that we have this formula for finding the slope, but the formula is in terms of a limit, right? And that means you have to take a limit, which requires, doing something. It's not as straightforward a calculation. Okay, so this is what we did last time, talking about the slope of the tangent line. And we also talked about a similar problem last time, which was this. So maybe before I go to the next slide, I'll just say indeterminate. So you need to do some simplification before evaluating. Because if you just evaluate, you get 0 over 0, and that's not helpful. Okay, so we had this other problem that looks like a different kind of problem. This was called the velocity problem. So suppose that we have a position of a particle moving in a straight line, and we're given, so as, say, as a function of time t is given by s equals f of t. Then what we showed was that the velocity of the object at time a is given by the limit as t approaches a of f of t minus f of a over t minus a. And this expression here, this is the average velocity between t and a. Right, this is the average velocity between t and a. It's the change in position divided by the change in time. So it's this velocity quotient. So if this limit exists, and then we can do the same change of variables that if you let h be t minus a, then you can rewrite this as the limit as h goes to 0 of f of a plus h minus f of a over h. And we observe that this is exactly the same as the solution to the tangent problem, right? So finding the slope of a tangent line is the same procedure as calculating velocity at a given time. Okay. So we saw that we had these two problems, both of which involve calculating something that's happening at one time or in one place, which is usually something that you need two times or two places to calculate. So for a velocity, usually you need to know how far have you gone in how much time. That's going to tell you two places. But in fact, we can use this calculus, we can use these limits to calculate what is the velocity just at one point, which is what the speedometer in your car is doing, right? It has to tell you how fast you're going right at a given point. You know, a speedometer on a car, a motorcycle, or whatever, it can't wait for now and 1 minute from now to see how far you've gone. It needs to tell you how fast you're going right then. And so it's this velocity problem is what's being solved for that. Okay. And so on the homework, we had an example of a tangent line calculation, and we have an example of a velocity calculation. And then we had a bit of a more conceptual question, which I'll want to talk about. Okay, so let's now that we've recalled this, let's go look at the homework examples. So the first example was, let's calculate the tangent line for the graph of y equals 1 over x at x equals 1. So it's always good to draw the graph first. This is x and y, and this graph looks like this. Y equals 1 over x. The graph looks like this if you graph it on a calculator or on Desmos or something like that. And if this is x equals 1, you have x equals 1 and y equals 1, right? Because x equals 1, you know, that this will give you that y equals 1 also. So we're at this point here, 1 comma 1, right? And the tangent line, you don't have to draw this to do the problem, but I'm just trying to draw it so that we can see visually what's going on. The tangent line looks like this, right? This is the tangent line. And we know that the tangent line passes through 1, 1. Okay. Okay. And so the key thing, we need to calculate the tangent line, but the key step, which we saw last time, the key step is calculate the slope of the tangent line. So this is our key step. And so to do this, we want to go back and use our formula, right? So the slope of the tangent line at this point, 1 comma 1, is we have to write down this limit, right? So I'm just going to copy it right here. What we're going to have to do is write down this limit. This is the limit as x approaches 1 of f of x minus f of 1 divided by x minus 1, where here f of x is equal to 1 over x. Okay? So what is this? So some people did this problem on the homework and used the power rule. That's okay, but I haven't taught the power rule yet. I'm going to teach it today. But let's show how we can do this using just limits, even if we don't know any rules, right? So you're not expected to know the power rule. So if f of x is 1 over x, this is the limit as x approaches 1 of 1 over x minus 1 over 1 divided by x minus 1. So this is a very complex fraction. So we need to simplify this to make it make any sense. So let's use, we have common denominator up here, right, is going to be x, right? So this is, maybe I'll use some extra space here. The limit as x approaches 1 of 1 over x minus, well, instead of 1 over 1, we can write x over x divided by x minus 1. And that we can write as the limit as x approaches 1 of 1 minus x over x, and that all divided by x minus 1. Okay, so this is a little bit complicated, right? And if you plug in a 1 here, you're going to get 0 over 0. So what can we do to simplify this expression over here so that we can evaluate the limit? So when we have a complex fraction like this, right, we have 1 minus x over x, and then we're dividing it again by something. How can we rewrite this as a simple fraction? Yeah,
I think we'll take the reciprocal of the denominator and multiply.
Okay, sure, that'll work, right? So we could do 1 minus x over x and then times the reciprocal of the denominator. So times 1 over x minus 1. Okay, that works. And what's nice about this is that we get a little bit of cancellation, right? The 1 minus x and the x minus 1 can basically cancel because 1 minus x is the same thing as the negative of x minus 1, right? So if we cancel the 1 minus x and the x minus 1, what we're left with is just a minus 1 when they cancel each other out, right? Because 1 minus x is minus 1 times x minus 1. When you have a subtraction and you multiply by minus 1, the subtraction flips, right? So what we end up getting that this is equal to is the limit as x approaches 1 of minus 1 divided by x, right? That's what this simplifies to. And now we can just plug in x equals 1, right? Because this now, the denominator is not 0 anymore, right? We made a cancellation. So now if you just plug in x minus 1, you just get a number, and that's going to be the limit, right? So this is just minus 1 over 1 now. Because remember, for a rational function, when you take a limit, you can just do that. If you want to factor out the minus 1 in the numerator, Enoch, that's fine also. That will also work. So in either case, you're going to end up getting minus 1 over 1, which is going to give you minus 1 for the slope. Okay, so the slope is minus 1. Right? And now what do we know? We have a line whose slope is minus 1, and that passes through the point 1, comma 1. So we can write the equation in point slope form. Right, is going to be y minus 1 equals minus 1 times x minus 1. Okay. And if you want to simplify this, this is y minus 1 equals negative x plus 1. And so sometimes if you want to get the y on one side, you just have y equals negative x plus 2. Okay. And so this is your final answer. So once you have the slope, we go over to here. Okay. And we should check realistically that y equals minus x plus 2 makes sense. does this look like a line that has slope -1 and y-intercept 2? Well, yeah, right? I mean, this line looks like it has slope -1 where it intersects the y-axis looks like 2, right? So this is at least, I mean, it's the correct answer. And also from just the way we draw it, it looks like it's the correct answer, right? Because it looks like this line should pass through y = 2, and it looks like it should have slope -1. So it's a good confirmation that we actually did the correct procedure here. Okay. So, right, remember, 2 steps. First, calculate the slope of the tangent line. That's going to involve some sort of limit. And then afterward, once you have the slope, then you can write down the equation in point slope form. Okay, any questions about this?
Hello, boss.
Yes, James.
I think that is clever. So that means if the derivative of the function is the same as slope, right?
Right. So you could say another way of writing this would be, I'll just put this in purple. You could say that, f prime of 1 is -1. So it's saying the derivative of the function at 1 is -1. Where here f of x is exactly this function 1 over x. Yeah. Other questions? Okay, great. Okay, so let's look at exercise 2. Same type of question, but now we're talking about physics. We're talking about velocity. So the position s of a particle moving in a straight line is described by this equation. S equals...
Hello.
Oh, hello. Yes, question? Want to go back? Yeah,
Yeah, that boss.
Yeah, I'm talking about Mandela. Yeah, it's actually bad. Back then in this one is in find this derivative that we use the limit of the function.
Yes. Sorry, yeah, I think I'm not getting you anymore. Okay. It must have something to do with the network. Okay, I'm sorry. Okay, if your network comes back, you can make a comment. I'm going to go to the next question. Okay, so now we have a physics question. So we have a position of a particle moving in a straight line is described by this equation. S equals t squared minus 8t plus 18, where S is measured in meters and t is measured in seconds. So so this is really 3 questions. So what is the average velocity of the particle between 3 seconds and 4 seconds? What's the instantaneous velocity at 3 seconds? And what's the instantaneous velocity at 4 seconds? So I'm going to divide our paper into 3 sections here. So we want the average velocity from t equals 3 to t equals 4. And here is going to be the instantaneous velocity at t equals 3. And here's going to be the instantaneous velocity at t equals 4. And again, some people submitted homework and they use the power rule to solve this, which is fine. But I'd like to do it without the power rule, partly because some people here probably don't know the power rule, and partly also because when we do these problems and we understand what's going on with the limits, when we do the power rule, we'll finally understand why it works. And I think we'll also appreciate it a little bit more because we'll see how it saves us from having to do this procedure. So let's start with this first question, and let's not use the power rule. So the average velocity from t equals 3 to t equals 4. Remember, this is not a calculus question, this first question, because it's not talking about what's going on at an instant. The instant and the limits is what makes it calculus. This here is just a physics and algebra question, because we're talking about the average velocity between t equals 3 and t equals 4, right? So we just have to set that up. it's just going to be the position at 4 minus the position at 3.
Hello?
Hello.
That over?
Yes, you came back. Yes.
Yeah, that was network message to walk all the way in the road. So
Sorry. Oh, wait. Is there somebody else?
Something.
Yep.
Yeah, something else from the previous problem.
Yep.
The problem number 1.
Mm-hmm.
Yeah, I thought in the solution we needed to have used the limit of the function when insert there, or s plus h, man on the function or h by h approaches 0.
Right. So you can do either one, right? We have two different formulas here that are both equivalent.
Okay.
Right.
Okay,
so we
okay.
use this top formula, but you could also use this one instead. They're both equivalent. Yeah. So you can use either one. Today, when we do the power rule, we're going to be usually using the second formula, as you say. But for evaluating a derivative at one point, sometimes the first formula is a little easier.
Okay. Yeah, because that was the one getting me. There was only 1 point given.
Right. So usually, I mean, again, you can use either one, but for 1 point, usually the first formula is easier. For evaluating it like as a function, the second formulation is usually easier. Okay.
Okay.
Great. Okay, so let's go back to this physics problem. So here we want to know what's the average velocity between t equals 3 and t equals 4, right? And so all that we have to do is this difference quotient, right? The change in position over the change in time, right? And so we just need to calculate what is S of 3 and what is S of 4. Well, we can do that, right? So S of 3 is 3 squared minus 8 times 3 plus 18. If you calculate this out, this turns out to be, so it's 9 minus 27 plus 18. So 9 minus 24 plus 18. So this turns out to be 3. And then S of 4 is going to be 4 squared minus 8 times 4 plus 18. So that's 16 minus 32 plus 18. And so that's going to be equal to 2. And so what we have is that S of 4 minus S of 3 divided by 4 minus 3 is just going to be 2 minus 3 over 4 minus 3. And this simplifies to -1. Right, so that means that the particle's moving -1 meters per second backwards. So, right, this is -1, and really, since I gave units, we should write a unit. It's -1 meters per second. Okay, so I did this one because this is not really a calculus question, right? This is just an algebra question. We look at the position at the final time minus the position at the initial time, and we divide by the amount of time that has gone by. In this question, that's 1 second. Okay, so that's the amount of time that's gone by. Okay, and there we are. Okay, any questions on this part of the question? No, this should be pretty clear. Okay, so how do we do, oh, sorry, question?
No, it's clear, it's clear.
Okay, good. Okay, so now how do we do the instantaneous velocity at t equals 3? We want to use this same limit procedure, right? With the velocity problem, right? So it's going to be a limit of this difference quotient as the time approaches 3. So what do we write over here? What limit do we have to do? It's going to be the limit as t approaches. Do it at 1 point, so we're going to use that first limit formula.
Yeah, we use this one. We use at t approaches 3, and the next one we use at t approaches 4.
Exactly. Right. So one of these is yeah. And what do we put in the fraction? Yep.
Yeah, the fraction we are putting the function.
Right. So S of t
minus.
So,
hello.
yes, hello? Yep.
Yeah. This problem. I think it would need it was needed to have been looked at, because this function, this is a function of time, so it's going to be s of t. S of t is equal to t squared.
It's going to be what? Sorry?
It has to be, I think it should have been s of t equal t squared minus 18 minus 8t plus 18.
Yes, that's right. Yeah, so I'll fill that in the next line. So s of t, though, minus, right, s of 3 here, right, over t minus 3. And if we actually write what this is s of t is given to us, right? So it's exactly as you said. It's t squared minus 8t plus 18. And then minus s of 3. We already calculated s of 3. That's equal to 3, right? So we're going to have minus 3 divided by t minus 3. And this is going to be the limit as t approaches 3 of t squared minus 8t plus 15 divided by t minus 3. And maybe just because we don't have that much space, we can factor this numerator, right? Because if you plug in t equals 3 here, you're going to get 0 over 0 again, right? You're going to get 0 over 0. Yeah, so how do we factor the numerator?
Yeah, the factoring method is that you are looking for two numbers, you will multiply, it gave you 15. If you add in the sum, should give you -8, which would be 5 and 3.
Right, so -5 and -3. Great. So t minus 5, t minus 3 over t minus 3. Good. And so now we can cancel the t minus 3s. That's how these limits always work. So we have the limit as t approaches 3 of just t minus 5. And that's, now we can just punch it in. That's 3 minus 5, and that's going to be -2 meters per second. Okay, so once you write this down and you cancel the factor, then it works, and you're left with 2 meters per second. So this particle at time equals 3 is moving backwards, right? It's moving backwards at a rate of 2 meters per second. That's what's happening instantaneously at time equals 3. Over the range from time equals 3 to time equals 4, it's moving backwards on average at 1 meter per second. But it's starting faster than that, right? It's starting by moving backwards at 2 meters per second. Eventually, it's going to slow down so that the average speed is only 1 meter per second. Okay, is this okay, though? Any questions on this problem? Okay, so no questions on this problem. Let's do the same thing for t equals 4, right? It's the exact same problem, right? Just with 4 instead of 3. So we have s of t minus s of 4 divided by t minus 4, which is going to be, if you write it all out, it's the limit as t approaches 4 of, again, we have t squared minus 8t plus 18, and now minus s of 4, which we calculated over here, is 2, right? So minus 2, all of that divided by t minus 4, and that's going to be the limit as t approaches 4 of t squared minus 8t plus 16 over t minus 4. And again, we have to do a factoring. So how does t squared minus 8t plus 16 factor?
Yes.
Yes, Prince, yeah.
We use -4 and -4.
Exactly, right. So t minus 4 and t minus 4 over t minus 4. So this simplifies nicely, and we get a cancellation there. And so we're left with the limit as t approaches 4 of t minus 4. And now this is a polynomial, so we can just punch it in. So this is just 4 minus 4, and that means 0 meters per second. Okay, so the instantaneous velocity at t equals 4 is 0 meters per second. So what's actually going on here is that the particle is moving backward at 2 meters per second at time 3, and it's slowing down by the time it gets to time 4, whereas at time 4, it actually stops. So it's gradually slowing down from 2 meters per second down to 0 meters per second. And so that the average speed over that interval is 1 meter per second. It's 1 meter per second in the backward direction. It's going from 2 slowing down to 0. On average, it's going at 1 meter per second during that time. Okay. So that's what's happening. Next week, we're going to talk a lot more about motion and calculus, and we'll draw all sorts of graphs and everything. But for today, we're just thinking about doing the computation. So when we do the computation, we just take these limits and we get different values for each of them. Yes, James?
Yeah, I'm kind of confused because then the first one has plus 8 plus 18, minus 18 plus 18. But now I say 16 minus 18 plus 16. How do we get like 15?
Right. Okay, good question, right? So the point is that you have, it's S of t minus S of 3 here, right? So the S of t is always t squared minus 8t plus 18. But we calculated that S of 3 here was 3, right? If you plug in 3, you get 3. So you have to subtract a 3. Whereas over here, it's S of t, which is still t squared minus 8t plus 18, but now you're subtracting S of 4, right? And S of 4 we calculated before is equal to 2. So here you're subtracting 2, whereas here you're subtracting 3. And so that's why at t equals 3, you get this 15, but at t equals 4, you get this 16, okay? Because you're subtracting a different position. You have the position at 3 versus the position at 4. Is that clear?
Yeah.
Okay.
Yeah, I understand. So I want to use the derivative, final derivative, but this is using the limit method.
Okay. What we're going to
Yes, sir.
do is we're
Yes,
going
sir,
to prove the derivative method using the limit method. That's what we're going to do today. And then we don't need to do this anymore. But somehow I think you need a foundation of what the power rule is based on. Otherwise, it's just magic, right? Somebody says, oh, you can do this power rule and it works. It's complete magic. Today, we're going to see, what's behind the magic. Okay. Any other questions? Okay, let's move on. Next one, we have a thinking exercise, not really a calculation. So the number of bacteria after T hours in a controlled laboratory experiment is N equals F of T for some function F. So what is the meaning of the derivative F prime of 5? And then the second thing says, if there's an unlimited amount of space and nutrients, which do you think is bigger, F prime of 5 or F prime of 10? And then if the supply of nutrients is limited, could this change your answer? Okay, so this is a bit more open-ended, this question, right? So let's look at the first question. What does F prime of 5 mean? Remember, we talked about derivatives last time corresponding to rates of change, right? So anybody give an explanation of what F prime of 5 means in this situation?
Yeah, hello?
Yeah, yep.
Yeah, my phone is about to go offset, but when this calendar was giving a number of bacteria after T hour, and the function giving is N is equal to F or T, which means the function is depends on a value is depending on the value of T. So if you see F prime of 5, it means that the function was somehow equal to N, and when it was where you differentiated for the first time, and you inserted 5, the value that comes out, which means it was between 5 to 6 hours.
Right. Or maybe even smaller, like it's like 5 hours and 5 hours and 1 minute, right? It's this rate of change over a very small interval of time at 5, right? Right. So what you're saying is exactly right. So this is the rate of change of the bacteria population How do we measure rate of change? It's in number of bacteria per hour, around 5 hours after the experiment starts. Right? Or you could say between 5 and 6 hours. It's a pretty good approximation for that because that's a small amount of time around 5 hours. Right. So, but you could say from 5 to 6 hours or 5 hours to 5 hours and 1 minute, whatever small interval of time near 5 hours that you want to do. But the point is that this is the rate of change of the bacteria population. This is the last thing we talked about yesterday, is that a derivative always represents a rate of change. Okay? For a graph tangent line, it could be the rate of change of the y value with respect to the x value. And for a velocity problem, it's the rate of change of distance with respect to time. And for something like the rate of change of the number of bacteria with respect to time. Yes,
hello.
Yep.
Yeah. What if I were going to say like the rate of change it will fall between 5 hours to 5 hours, like the 5 hour 15 minutes? Will I be correct between 5 hours and 5 hour 15 minutes?
Yeah, everything here is approximate, right? So there's lots of answers that are close enough to correct. So 5 hours to 5 hours, 15 minutes, 5 hours to 5 hours, 1 minute, 5 hours to 5 hours and 5 seconds would be fine. What it really means is it means the limit as these intervals get smaller and smaller. But if we're just roughly thinking about it like a scientist instead of like a mathematician, what it means is that around time 5 hours, this is the rate of change. And you can put in your favorite interval as long as it's pretty small. Yeah. Okay. So now, so that's f prime of 5. So now here's a question. So let's say that we're in this big tank. We have a small bacteria population and lots of food and lots of space. So the question is, when is this rate of change higher? Is it going to be higher after 5 hours, or is it going to be higher after 10 hours? Okay, so this is maybe f prime of 5 versus f prime of 10. So what do we know about how bacteria grow? So this is a little bit of a biology question, I guess. But what do we know about how bacteria grow?
Yeah, so hello?
Yeah, hello. Yeah.
Yeah, it's like in this method, like I explained previously, and this function was differentiated only one time, and the inserted value, which is the value for the function of t that you put there, it was 5. And now we have this, we have it going against when the same function was also differentiated and you put the value of 10. So if this first one it will fall between 5 and sometime later, this one will also 10 and sometime later. So in this method, it will be the f prime of 10 it will be higher than f prime of 5.
Right. So why? Can we come up with? I mean, I'm asking. Can I come up with a biological explanation for this? Right? Because this is modeling, right? I mean, so what we're doing here, right? This is not just a math question, because we want to be using this math to model science, to model the world, right? So this is saying, so after 10 hours, so what do we know about how bacteria reproduce? So little biology, right? Bacteria reproduce by splitting, right? Yes.
Yeah, let me try to say something if it really makes sense, because I was thinking it to do. So this one, it tells us that for the 10 hours, the bacteria will like increase in production. Am I right?
Yeah, right. There's definitely more bacteria after 10 hours than after 5 hours, right? Because they've split. Yeah. So there's more after 10 hours. And when you have more bacteria, remember the bacteria just split every once in a while. Every so often they split, right? So if you've got more bacteria, then the rate of reproduction should also be higher, right? Because the more bacteria you have, kind of the rate of growth is proportional to what you have. This is what's called exponential growth. We'll talk about this probably not this semester. We'll talk about it next semester. But the bacteria, the more you have, the faster it grows, because each of your bacteria could split any minute, right? And so if you have more, there's more that are splitting at any given time. And so the rate is higher, right? So Enoch, you're exactly right. So f prime of 10 should be bigger than f prime of 5, because more bacteria after 10 hours means more splitting, which means faster growth. Okay. Sorry. Right, so more bacteria after 10 hours means more splitting, which means faster growth. And so remember, this derivative represents a rate of change. So we're saying that the rate of change at 10 hours should be faster than the rate of change at 5 hours. This is assuming we have unlimited space and unlimited nutrients, right? But now imagine these bacteria are maybe in a small petri dish and there's only some food in the dish, maybe not lots of food, just some food. And maybe as we get toward 10 hours, the carrying capacity of the dish starts to get exceeded by the number of bacteria, right? So Kaifala asks, what if the space and nutrients are limited? So what if space and nutrients are limited? So what might happen here? Again, it's an open-ended question. It's not that there's one correct answer, but there's maybe an idea that should be coming through in this answer.
Yeah, hello?
Yeah. Yes, hello?
Yeah, I want to give my own input.
Sure.
Yeah, if there were the space nutrient were in only limited, it means that then it means that you will have 10 hours, it will produce more, and 5 hours it will produce less. Even if it is not effective, 10 hours will still produce a bit more than the 5 hours.
Right. So maybe there are still more bacteria at time 10 than at time 5. The question is, if bacteria are starting to die because there's no food left, then maybe that rate of increase is going to slow down. Or maybe not. Maybe the supply of nutrients is limited, but there's still enough that at 10 hours, they're still producing very widely. So, I mean, the answer is we don't know. We don't know, but it is possible that if the population, bacteria population, is close to the carrying capacity, of the amount of space and the amount of nutrients, then it's possible that f prime of 10 is less than f prime of 5 because population is starting to grow slower. Right? Or it's possible that f prime of 10 is still bigger than f prime of 5. Maybe we're not that close to the carrying capacity. I haven't told you what bacteria they are. I haven't told you how much food. There's a lot more information you need to be able to get a definite answer to this question. But just in terms of the basic concepts, the idea is, well, if you're getting close to the carrying capacity, then the rate of increase is going to start to level off. Maybe the bacteria reach some equilibrium with their size. And that means that they're not growing fast anymore. It's kind of staying the same. Or maybe they're even really starting to die off. Maybe the rate of change even becomes negative. That all depends on how close to the carrying capacity we are. So if there's unlimited space and nutrients, then of course f prime of 10 is going to be bigger than f prime of 5. The rate of change is going to be higher at 10 hours. But if we're getting close to the end, then maybe they could be the same. Maybe f prime of 10 could even be lower, or maybe it's still higher. We just don't know without more information. Okay. Is that okay?
Yeah.
Okay, great. Any questions? Okay, great. Okay, so that's enough for homework. Let's move on to new stuff. So let me just recall, we talked about the tangent problem and the velocity problem. I didn't use the word derivative, but the derivative is what encodes this common solution of both the tangent problem and the velocity problem. So we talked about this last time. So if f of x is a function, we say that the derivative of f of x at x equals a, and we write that as f prime of a, is we have two equivalent formulas for it. You can say it's the limit as x approaches a of f of x minus f of a over x minus a. Or you could say it's the limit as h approaches 0 of f of a plus h minus f of a over h. And this derivative gives the slope of the tangent line to y equals f of x when x equals a, and it also gives you the solution to this velocity problem. Okay, so this is still review from last time. This is what we talked about. So in particular, last time we only talked about the derivative at a particular point. So we said at some point x equals a, this f prime of a is given, and I want to focus now on the second formula. So given by f prime of a equals the limit as h approaches 0 of f of a plus h minus f of a over h. Okay. So I want to think now of a as being, okay, you're punching in some value of x here. But you could really, a can be anything, right? Just like in our physics problem, we talked about, in this case, s prime of 4 and s prime of 3. We could have asked what happens at t equals 2. We can do any time we want. So what I really want to do is think of this derivative actually as a function. Remember what a function is. A function has an input and gives an output, or it has inputs and it gives an output for each input. So I want to think of a here as the input and this limit as the output. And that's going to be a new function, which we call the derivative. So what I'm going to say on the next slide is that if we replace a with a variable x, so we allow to think of it as a function instead of just at one particular value, then we can define the derivative f as a function. I should say, sorry, this should be f prime of x. So this function inputs a value a and outputs the value f prime of a. And we call this f prime of x, and we call it the derivative of f. So as a formula, maybe I'll just say as a formula here, f prime of x is equal, this is definition, to the limit as h approaches 0 of f of x plus h minus f of x divided by h. Okay, so this is exactly the same formula that we had for the derivatives, but instead of an a, we have an x. And of course, nothing changes. You're just changing the letter. But the idea is you're thinking of x now as a variable that can be any number, whereas a we were thinking about as one specific number. So the only difference here is that now this x is being thought of as a variable, not as a particular number. Okay. So I should say the act of finding a derivative of a function is called differentiating it. So sometimes you'll hear somebody say differentiate the function. That means take the derivative of the function. Okay. And so there's other notation that's sometimes used. So sometimes this notation d dx is used for a derivative. So you'll see this in the book. So saying d dx of a function f is the same thing as saying f prime of x. It's the same thing as saying take the derivative. So maybe before we do the example, yes. So Hassan said exactly right. If nutrients in space become limited, the growth rate will plateau, so it'll go down to 0, and then eventually will lead to a sharp fall in population growth. So it will become negative. So for the previous question, the question is, at time equals 10 hours, has the growth rate plateaued yet, or is it still increasing rapidly? And I didn't give you enough information to know that. So the answer is just, well, we don't know. It depends on how close to carrying capacity we are. Sorry, Enoch, did you have a comment?
Yeah, I wanted to say something like for this one, because this is the basis on find that I think you should have given some vivid information about getting the difference between dy by dx, f of x, f prime of x, or y prime of x. Because sometimes in other words, instead of me writing dy by dx, or instead of me writing d square y or dx square, or instead of me writing all those stuff, I'll just write like y prime. Or sometimes I'll write y prime prime. So sometimes it may contradict some people. So I think you should put it down here, note f of x, because sometimes like the area you see f of x equal x squared. Sometimes in finding the derivative, I will just write it as y equal x squared, then I say y prime. Someone may want to ask, why should you put y, or why you put y prime?
Sure.
So I think so.
Okay, yeah. I mean, so there's even more notations. I'm introducing two of them now. There are other notations. So if y is equal to f of x, then you can write y prime is f prime of x. So this is just more notation. Or you can write Or you could write dy dx equals f prime of x. So all of these things mean the derivative. To say f prime
Okay.
of x, to say y prime, to say dy dx, or to say ddx of the function, they all mean the derivative. And we're going to use all of them because it's good to recognize all the notations. For now, I'm just introducing the notations slowly. So up until now, we had only this notation f prime of x. I'm now introducing ddx also, and I'll introduce the other two. We'll work them in as we do more examples. Okay, but yes, to know that there are really 4 different notations you can use for the derivative. And part of this is because calculus was developed, by Newton and Leibniz separately, and so they each had their own notation for how to do the derivatives, and now we have all of them. Okay, so this is the function to take the derivative. So a simple example would be if f of x is x squared, let's find its derivative not at any particular value, but as a function. So for instance, what do? Well, we have to use this definition. So what is d dx of x squared? Well, using this limit, it's the limit as h approaches 0 of x plus h squared minus x squared over h, right? It's f of x plus h, which means x plus h squared, then minus f of x, which means x squared, divided by h.
Yeah, sure.
So remember, we have the binomial theorem for expanding x plus h squared. That's x squared plus 2xh plus h squared minus x squared divided by h. Or in other words, the x squareds cancel each other out here, and we're left with 2xh plus h squared divided by h. Or we can simplify this because h is a factor of the numerator and of the denominator. So this becomes 2x plus h over 1. Okay, so I'm sorry, I'm running out of space. So what we get here is the limit as h approaches 0 of 2x plus h over 1. That's just 2x plus h. And so we can take the limit as h approaches 0 of this function, and nothing happens to the 2x, but the h approaches 0, so it just disappears, and this gives us 2x. Okay, so this tells us that the derivative of x squared is going to be 2x. And that means the derivative of x squared at like x equals 3 is going to be 2 times 3. It's going to be 6. So as a function, the derivative of x squared at any x value that you plug in is going to be 2 times that value. Okay? So we're just doing this limit, but with a variable x instead of a constant h. Instead of a constant a. So if x is equal to 3, that would be like plugging in a equals 3 here, and you'd end up getting 6 as your final answer. But instead, we just have x by itself as a variable, and so our final answer will also be a function in terms of x. So in this case, we have 2 times x. Okay. Okay, so this is a simple example. And what we want to do is get some rules for being able to take derivatives. Okay, so we want some rules for, so that we don't have to do a limit every single time we want to take a derivative. We want some formulas that will make our lives easier. Okay. And so this is the question. So are there better ways to compute derivatives than what we've been doing? The answer is yes, right? Evaluating a limit every time you want to compute a derivative is inefficient. And for the standard functions, there are rules that will tell you how to compute a derivative without actually doing a limit every single time. And the most important rule is what's called the power rule. Okay, and we're going to spend most of today discussing the power rule, and we'll talk about a couple of other rules. Okay, so this power rule that some of you already know because you've been doing it on the homework, but I want to derive it so that everybody can use it. Okay, so how does the power rule work? Well, before we derive the power rule, we need to do a little bit of algebra. Okay, so I need to recall what we call the binomial theorem from algebra. And for this, we need some notation. So first, if n is a natural number, we define n factorial. This means and we did this when we did probability last year, if you were here. that n factorial is the product of all of the natural numbers up to n. So for instance, 3 factorial is just 3 times 2 times 1, which is 6. 4 factorial is 4 times 3 times 2 times 1, which is 24, and so on. So that's what these factorials are. And one little bit of convention is that's going to be kind of important, is that 0 factorial is equal to 1. And we really think of this as a definition. Okay, so 0 factorial is equal to 1 by definition. Okay, you might think it would be 0, but it actually turns out to make much more sense to have 0 factorial be 1. Okay, so this is n factorial, and we use an exclamation mark to symbolize it. And you multiply all the numbers up to n. And then the other thing is we define these binomial coefficients. Sorry, this should be k. For n greater than k greater than or equal to 0, this binomial coefficient here, which is sometimes read n choose k, or sometimes just nck.
Yeah.
Yeah. Yes, Prince?
Yeah. As you said, 0 factorial is equal to 1. Was there any way by means that 0 factorial being equal to 1? Like, if there's any proving method that show that 0 factorial is equal to 1, or is just by definition in mathematics?
I mean, so that's a very good question. It's basically by definition, but you can ask, why is that a good definition? And the reason why it's a good definition is the following pattern. If I take 3 factorial divided by 3, this should be equal to 2 factorial, right? Which is 2. And then I have 2 factorial, because 3 factorial is all of this, and I divide it by 3, what I'm left with is 2 factorial. So then 2 factorial, if I divide that by 2, that should be equal to 1 factorial, which is 1, right? Because 2 factorial is 2 times 1, and if I divide it by 2, I should just be left with 1, which is 1. So if we continue this pattern, we should have that 1 factorial divided by 1 should be 0 factorial, right? This is the pattern here. 1 factorial divided by 1 should be 0 factorial. Well, this side is 1, so this side should also be 1. This is maybe a justification of the definition. It's a reason why the definition is good, because the definition allows us to continue this pattern that n factorial divided by n is n minus 1 factorial. Okay, so if you repeat this pattern, you end up getting that 0 factorial equals 1. Okay, so it's a nice reason. But ultimately, it's a definition. But this is what justifies the definition. Okay. Is that okay, Prince?
Thank you so much, sir.
Great, you're welcome.
Yeah.
Okay, great. So we have this binomial coefficient, which is this quotient of these various factorials. So an example would be if I had, 4 choose 2, this would be 4 factorial divided by 2 factorial times 4 minus 2 factorial. Well, 4 factorial we already know is 24. 2 factorial is 2. 4 minus 2 factorial is 2 factorial, which is also 2. So this turns out to be 6, just as an example. These binomial coefficients have meaning in probability. We've talked about it last year. Maybe not everybody was there, but this is the number of ways of choosing a committee of 2 people out of a group of 4 people. So if 4 people are gathered in a room and you want to pick 2 who are going to be, like the presentation leaders for the group, there's 6 ways of picking those 2 people. Okay, so this is one of the meanings of n choose k. It's a number of ways of picking k people out of a group of n people as a group. But I'm not going to derive that. I mean, I'm not going to justify why this is the formula for that. When we talked about probability, we spent a little bit of time on this. But for now, I just want you to know that this is a formula, and you can evaluate it using factorials, and it has some meaning. And I guess I should also mention that if I take any n, choose 0, how many ways are there of picking 0 people? Well, basically, by the definition here, that's n factorial divided by 0 factorial times n factorial. And remember, by our convention, 0 factorial, right, because it's 0 factorial and then n minus 0 factorial. So by convention, 0 factorial is equal to 1. And so this is just equal to 1 over 1, which is 1. So no matter what number you have, if you do that number choose 0, you get 1. And in fact, also n choose n is also going to be equal to 1. Actually, I want to make sure. Yeah. Okay. All right. And well, I don't have space for this, but on the next page, let me actually just do one more example. So on the next page, I want to just do what happens when you do n choose 1. This is going to be important. So n choose 1 is going to be n factorial divided by 1 factorial times n minus 1 factorial. And well, what is this? This is n times n minus 1 times everything down to 2 down to 1. And then divided by, well, 1 factorial, which is just 1. And then you have n minus 1 factorial. So n minus 1, n minus 2, all the way down to 2 and to 1. And in this fraction, you get lots of cancellation. The n minus 1 and the n minus 1. There's an n minus 2 and an n minus 2. The 2 and the 2, the 1 and the 1. And what you're left with is just this n over 1. So what this is actually equal to is n over 1, which is n. So this is going to be important to us, that n over 1 factorial is equal to n. Sorry, it's that n choose 1 is equal to n. And with this, interpretation, that makes sense, right? Because the number of ways of picking one person out of a group of n people is exactly n. You can choose any of the n people to be that one person. Okay, so n choose 1 is always equal to n for any number n. That's going to be useful to know. Okay, so this is our binomial coefficients. They're going to be important for what we're doing. We're eventually going to use this for calculus, but for now, this is just a review of the algebra of what are called binomial coefficients. Okay, any questions about this? All right, so let's go on. All right, so what is the binomial theorem? So the binomial theorem, we already did this for a square, but it tells you how to do the expansion of x plus y to any power. That's what the binomial theorem tells you. So if you have x plus y and you want to raise it to the 3 or to the 4 or to the 5, well, this tells you how to do it. So in summation notation, this is maybe a little bit opaque to read if you haven't seen it before, but it's the sum from k equals 0 up to n of this n choose k, this binomial coefficient, times x to the n minus k times y to the k. And maybe more explicitly, if you want to write this out without the summation notation, what that is that x plus y to the n is going to be what happens with k equals 0. You get n choose 0 times x to the n times y to the 0. So that's just n choose 0 times x to the n. Then the next term is n choose 1 times x to the n minus 1 times y to the 1. So n choose 1, x to the n minus 1, y to the 1. And then we keep going. N choose 2, the next term, if we had to write it down, would be, n choose 2, x to the n minus 2, y squared, etc. And then we get to the last terms, which is n choose n minus 1, x to the 1, y to the n minus 1. And then the last term is n choose n, x to the 0, y to the n. Okay. So for instance, just as an example, if n is equal to 3, this tells us that x plus y cubed is equal to 3 choose 0, x cubed, plus 3 choose 1, x squared y to the 1, plus 3 choose 2, x to the 1, y squared, plus 3 choose 3, y cubed. And well, what is this? Well, we've already seen that 3 choose 0 is equal to 1. So that's x cubed. We've already seen that 3 choose 1 is equal to 3. So that's 3x squared y. What about 3 choose 2? Well, maybe you know this, but let's just do it. 3 choose 2 here is going to be 3 factorial divided by 2 factorial times 1 factorial. This turns out to be 3 also when you do 3 choose 2. So this is going to be plus 3xy squared. And lastly, 3 choose 3. I'll leave it as an exercise. This turns out to be 1. So we end up with x cubed plus 3x squared y plus 3xy squared plus y cubed. Okay. And you can do the same thing for raising to the fourth or raising to the fifth or raising to the sixth and so on. And in fact, if you're familiar with Pascal's triangle, then what these coefficients are is actually just for x plus y to the third, the coefficients are just the third row of Pascal's triangle. For x plus y to the fourth, the coefficients are just the fourth row of Pascal's triangle. And for x plus y to the fifth row of Pascal's triangle, and so on. Okay, so this is the binomial theorem. It tells you how to multiply out a sum of two terms. That's why it's called binomial theorem, because we have two terms. And if you raise that to the n, this is actually what you get. When n equals 2, you get your familiar formula, x squared plus 2xy plus y squared. Okay. Okay. So here I have examples of the binomial theorem. Maybe I won't write down so many examples, but let me just show you, if you haven't seen it or if you don't remember it, Pascal's triangle. What's Pascal's triangle? It's a triangle where you start with writing ones down the sides like this, and then each entry is the sum of the two entries above it. So here you get a 2 because it's the sum of the 1 and the 1. Here we get a 3 and a 3 because the 3 is the sum of the 2 and the 1. And here we have 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, right? Each entry in the triangle is the sum of the two entries above it. And we could do another row if we want to, 1, 5, 10, 10, 5, 1, maybe even one more row, 1, 6, 15, 20, 15, 6, 1. You can keep going, 1, 7, 21, 35, 35, 21, 7, 1, and so on. And it turns out that the coefficients of x plus y to the n exactly correspond to the nth row of Pascal's triangle. Okay, so where you have to just have this coefficient, this convention that the first row is actually called the 0th row, and then you say the first row, and then the second row, and the third row, and so on. So, right, so we already see this, right? I mean, if you have x plus y squared, you get x squared plus 2xy plus y squared, right? 1, 2, 1 are the coefficients. For x plus y cubed, we've seen we get 1, 3, 3, 1. That's what we get on the previous one. So for instance, if we had x plus y to the fourth, it turns out what we're going to get is x to the fourth plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus y to the fourth. Okay? You can do this with the binomial theorem, calculating all these binomial coefficients. But if you're trying to do it for speed, it turns out that when you raise it to the n, what you're getting is exactly the coefficients in the nth row of Pascal's triangle. That's how this works. Okay. All right. So this is the binomial theorem. Why do we care about binomial theorem? Well, we care because it's what's going to allow us to derive this power rule in calculus. So we're going to go back to calculus in a minute. But before we do any calculus, any questions about binomial theorem, how we do these expansions?
Yeah, for me, all is clear. Is really
Okay.
clear.
Good. Anybody else? Any questions? Okay. All right. So let's move on. Okay. So what's the power rule? So let's try to calculate the derivative of x to the n, where n is a natural number. And so remember that this is our formula for the derivative. It's given by this limit. The limit as h approaches 0 of f of x plus h minus f of x over x. So let's write what this is. This is the limit as h approaches 0 of x plus h to the n minus x to the n divided by x. Okay. Now, what happens when we expand this out? Well, now we have this x plus h to the n. So we're exactly using our binomial theorem. So if we go back to what the binomial theorem is from x plus y to the n, the first term is x to the n. The second term is going to be n. Remember, n choose 1 is always n. And then we're going to have an x to the n minus 1 and a y. And then we have some other terms that will all have a power of y, which will be h in our case, of at least 2, right? The next term's got y squared and then y cubed, y to the fourth, and so on. So going back to our slide, if we write this down, what is this? Let me give myself a little more space to write this. I don't want it to be too small. This is going to be x to the n plus n x to the n minus 1 h. These are the first two terms. And then we have some more terms, plus n choose 2 x to the n minus 2 h squared, plus so on. In the end, we get to n choose n minus 1 x times h to the n minus 1. And then the last term is n choose n h to the n. That's all the x plus h to the n. And then we subtract an x to the n, right? So we're going to have a minus x to the n. And then, oh, sorry, this is a typo here. This should be an h. And this is a typo here. This should be an h. Okay. That's an h in the formula. And so we divide this all by h. So we can do a small simplification now, right? We've got x to the n and x to the n cancel each other out. So this is what we get the limit as h approaches 0 of n x to the n minus 1 h plus n choose 2 x to the n minus 2 h squared plus so on. And I'll just write the last term, n choose n h to the n. All of this over h. Okay. Well, this is really nice because we had the x to the n and the x to the n cancel each other out. And so now we have a fraction that is not in lowest terms, right? If I plug in h equals 0, every term up here has an h. So they're all going to be 0. And the denominator is h. So it's going to be 0 also. But what we can do instead is we can cancel out an h, right? Because there is an h. We can factor out an h in this numerator, right? This is h times n x to the n minus 1 plus n choose 2 x to the n minus 2 h plus all the way up to h to the n minus 1. That's the, or yeah, so n choose n. Sorry, it's no space to write this. Try to do plus dot 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 plus n choose n h to the n minus 1. Sorry, this is small, divided by h. And now when we cancel out these h's, we end up getting that this is the limit as h approaches 0 of n x to the n minus 1 plus n choose 2 x to the n minus 2 h plus, now maybe I'll write one extra term. This is n choose n minus 1 x h to the n minus 2. And then the last term is n choose n h to the n minus 1. Right? I'm just writing out all of these terms. Okay? And now that I've taken one factor of h out. All right, well, what happens as h go to 0? Well, all of these terms disappear. It's just a polynomial. All of these terms disappear, and I'm left with just nx to the n minus 1. So the final answer here is just nx to the n minus 1, because as h goes to 0, all of these terms disappear. And so we're left with just nx to the n minus 1. Okay, which is going to be, one second. Okay. Yeah. So yes, question, Emmanuel.
Oh, you're going to be.
Yeah. So this is what we have. So when we calculate this limit, we've got all these h's and x's and n's floating around. It's a little hard because you don't have any numbers, but what you finally end up with is n times x to the n minus 1. Okay? And this is what's called the power rule. So we're saying that the derivative of x to the n is equal to n x to the n minus 1. Right over here, everything just as the h goes to 0.
I told Messi already.
Sorry.
But besides, she coming to school tomorrow.
Okay. Okay, so this is maybe the most important formula in calculus, right? So the derivative of x to the n equals n times x to the n minus 1. And this is where it comes from. It comes from taking this limit and expanding this expression using a binomial expansion, okay? And when you use the binomial theorem, you cancel out these x to the n's, you then cancel out a factor of h, and then you let h go to 0, that all of these complicated terms disappear, and what you're left with is only this one term at the beginning, this n times x to the n minus 1, okay? And so that gives you this formula, which is called the power rule, okay? Okay, so any questions on this? Let's see, yeah. And so, by the way, look at this example that we did before. We saw that the derivative of, we go back here, right, we did this, the example was the derivative of x squared equals 2x. Now we can see from the power rule, this is much easier, because how do you do x squared? You bring the 2 down, and then you decrease it by 1. So it's 2 times x to the 1, which is exactly 2x. So this is an example of the power rule, right? So you should think of the power rule as you bring the n down, and then it's replaced with an n minus 1. So if we see these examples of the power rule here, right? So this is, I'm just stating the theorem. This is the power rule. If f of x is x to the n for a natural number n, then f prime of x is n times x to the n minus 1. So we have, x to the n. What do? You bring the n down here, and then you replace it with an n minus 1. Okay, that's how you should think about it as the power rule. Okay. And in fact, although I'm not proving it now, the power rule works for any number n. What we proved was only for a natural number because we used this binomial theorem. But in general, the power rule works for any exponent at all. So it works for negative numbers, it works for fractions, it works for irrational numbers, it works for anything at all. You always have that, if you have the function x to the n, the derivative is n x to the n minus 1. Yes, Enoch?
Yeah, so they want it work in any form, or except where n is not equal to 0.
Even when n is equal to 0, it still works.
Wow,
it still works.
Seriously?
Yep, right. Let's do that, right? Okay, let's do, that's a great example. So if f of x is equal to x to the 0, right, which is just 1, then what the power rule tells us is that f prime of x is equal to 0 times x to the 0 minus 1, right? Which is 0 over x, which is just equal to 0. And this is true.
So which means hello?
Yep.
Yeah, so which they seem as funny when n is equal to 0, it seems as funny the derivative of a constant.
Right. Exactly. And so let's do that explicitly. So right, in general, derivative of a constant
is 0. It's always 0.
Always going to be 0, right? Because what's the derivative of f of x equals c? Well, what do we have? Well, remember, it's the limit as h approaches 0 of f of x plus h minus f of x over h. But if f is just a constant, this is just the limit as h approaches 0 of just c minus c over h, which is the limit as h approaches 0 of 0 over h. And well, 0 over h is always 0 for all non-zero h, and that's what you have with a limit. So this is just 0, right? So the derivative of a constant function is always going to be 0. That kind of makes sense because a constant function is a flat line. And remember, the derivative gives you the slope of the tangent line, so it's always going to be horizontal. It's always going to have slope 0. That's another way of seeing this. But the power rule also works. You can think of it as the power rule, and it gives you the right answer. So the power rule works, completely well. So if f of x... Sorry, let me just do one more example. So if f of x equals x to the minus 1, then f prime of x, power rule is just minus 1 times x to the minus 2, which is the same as negative x to the minus 2, or if you want to write it in a different way, you could write that as negative 1 over x squared. Okay, so this is one way you can use, so the power rule works here even with a negative exponent. You get negative 1 over x squared. And remember, our first homework example today, this was our function, and we evaluated this at x equals 1. And the answer we got was negative 1. And that's exactly what you get by this formula. If you punch in x equals 1, you get negative 1. It's negative 1 over 1. Okay? So the power rule gives you the right answer there also. But proving it for general n is harder. I'm not going to do it today. For natural numbers n, you can use the binomial theorem. To prove it for negative numbers or fractions is a little bit harder. So I'm not going to be able to do that proof today, and probably not even this semester, maybe sometime in the spring. But I'll tell you that it's correct. So
even
you can use it for any n.
For proving for natural number, which is when you have a negative exponent, I can do it too.
Okay.
Long.
Yeah, it requires you have to use the quotient rule or implicit differentiation, or that there's various ways of doing it, but it's not as straightforward. Yeah, so I wanted to show only the more straightforward proof today, which is the natural number case. Okay. And that's the most important case anyway, because polynomials are what model most things in nature, right? I mean, other exponents are important also, but polynomials show up the most. And that's when you have natural number exponents. Right, questions? Okay, so let me give you just a couple of other basic rules for taking derivatives. So this says, let's say that I have a function f of x, and g of x is that same function but multiplied by a constant. Then what I claim is that g prime of x is equal to that constant times f prime of x. So multiplying a function by a constant multiplies the derivative by the same constant. So as an example, let's say that we have f of x equals 3x squared. Sorry, f of x equals x cubed. That means that f prime of x by the power rule, the derivative is going to be 3x squared, right? We bring down the 3, and what we're left with is a 2. If instead that I have g of x is maybe equal to 5x cubed, so if I multiply the function by 5, then the derivative should also get multiplied by 5. So if the derivative of x cubed is 3x squared, then the derivative of 5x cubed, g prime of x, should be equal to 5 times 3x squared. Or in other words, 15x squared. Okay? So when we multiply a function by a constant, it multiplies the derivative by the same constant. Right? And ditto, and again, that constant can be anything. It doesn't have to be a natural number. So if h of x was equal to like negative 1 over pi times x cubed, then h prime of x is just going to be negative 1 over pi times 3x squared, or negative 3 over pi times x squared, so etc. Right? So all of these multiply by a constant, you just multiply the derivative by the same constant. Question?
The question.
Yeah, Prince? Yeah.
So, okay, yeah. It's not a really question. I think I'm assuming. Pi, we'll have a g of x equal to pi x raised to the k power. So that gets me because it's duality. We took the power of 3 and then multiply by 5 and then subtracted 1. Is that what we do?
Yep. That works.
So we say 3 to 5 and minus 1 from the 3, right? So I'm saying.
Yeah, so that's fine, right? Yeah, you only subtract 1 from the exponent, and then you bring the 3 down, but if there's an extra 5 here. And what this theorem says is that extra 5 carries through to the derivative. So you've got to also multiply the derivative by 5. That's why you get the 15 over here.
Okay.
Is that okay? All right, questions? Okay, this one I'm going to prove because the proof is not that hard. So we want to calculate, so g of x is equal to c f of x. I want to calculate the derivative of g. So let's just do it. So then g prime of x, we have a formula for this. It's the limit as h approaches 0 of g of x plus h minus g of x over h. Well, g is just c times f. So this is just the limit as h approaches 0 of c times f of x plus h minus c times f of x divided by h. And now I've got an extra c here. And c is a constant that divides this numerator. And we know that we can pull constants out of limits, right? The limit of a constant times some function is just that same constant times the limit of the function. So this is equal to c times the limit as h approaches 0 of f of x plus h minus f of x divided by h. And now, what is this whole thing here? This whole thing here, by definition, is exactly f of x. Sorry, is f prime of x. So in the end, you get that this is c times f prime of x. Okay. Right, so so this is the proof, right? If you just try to take the derivative of g, you just end up getting a c times the derivative of f. So this is telling us that g prime of x is equal to c times f prime of x. So you multiply f by 5. That means you're multiplying its derivative by 5 also. Okay, because that 5 or that c, whatever number you want, is just there in the limit, and you can just take it out. And you get this extra factor of c. Okay. So the g prime of x is equal to c times, if g of x is c times f of x, then g prime of x is c times f prime of x. It's going to be the same thing. You just have an extra constant. Okay. Questions? So yeah, it's worth doing this proof because it's only 2 lines long. Again, it's not just magic. It's not just, well, of course, if you multiply a function by c, its derivative gets multiplied by c. It has a proof. But it also makes sense if you think about it as kind of in terms of velocity, right? If you have a position function and you multiply the position function by 2, then you're also multiplying the speed by 2, right? If every position is getting multiplied by 2, then your change in position is also getting multiplied by 2. So your speed is getting multiplied by 2. That's maybe the physics intuition behind this. But the math is irrefutable. You just calculate this limit, and you've got an extra c. Okay. Okay, so 2 more basic rules. These are going to be all the rules we have for today, and then we'll see how we apply them. Excuse me. So let's let h of x, let's say we have 2 functions, f of x and g of x. And let's say that h of x is either their sum or their difference. I have this notation here that's plus minus. So it just means that this works for plus and it also works for minus. So if h of x is f of x either plus or minus g of x, then h prime of x is f prime of x plus or minus g prime of x. So in other words, the derivative of the sum is the sum of the derivatives. So one way of seeing, so an example of this would be something like d dx of x cubed plus x squared. If we have 2 things like this, well, then all that we have to do is take the derivative of each term and add them. So the x cubed would become 3x squared. The x squared would become 2x. And same thing with minus, right? If I had d dx of, x to the 6th minus x to the 4th, this would just become 6x to the 5th minus 4x cubed. Okay? Okay. So if you have a sum of 2 terms or a difference of 2 terms, you can just take the derivative of each term and do the sum or do the difference. So you can do them one by one. I think maybe I won't do a full proof of this. Sorry, yes, Enoch?
Yeah, what if in this final derivative I see 3x squared plus 2x? What if I want to factor out the other x because I want to simplify to a large extent?
Sure. Okay. I mean, if we want to, we can pull out an x here. This is x times 3x plus 2. Or if I want to simplify here, we could pull out an x cubed, and this would be x cubed times 6x squared minus 4. It's fine.
Yeah.
If you want to do it, you can do it. Yeah.
The last one, you got to pull out 2x cubed.
Sure. Okay. Yes. You can go even further. Sure. 2x cubed times 3x squared minus 2 if you want to. Yeah, that's fine.
Yeah. Sure.
Yeah, so that's fine. Maybe I'll skip the proof of this, but maybe I'll get you started and you can finish this up for yourself. So I'll do maybe one case. So let's say that h of x is equal to f of x plus g of x. Then, h is a bad letter. Let me use a different letter. Let me call it j, because we already have the letter h in the derivative definition, so maybe I'll use a different letter. So then what is it? Well, j prime of x is equal to the limit as h approaches 0 of j of x plus h minus j of x divided by h, which is f of x plus h plus g of x plus h, right? Because j is f plus g, minus f of x plus g of x divided by h. And the exercise is, can you finish this proof? It's an extra credit homework problem.
Hello?
Yes, hello, Enoch?
Yes, I can do it.
Okay, maybe don't do it in front of the class. Let's let everybody think about it. We can present it next time. Okay?
Okay.
Okay, so you can either write it down and send it to me, or you can do it for the class next time. But I want to give people a little bit of time to think about how to do this. So you want to simplify this limit and somehow get that it ends up with the formula you want, which is f prime of x plus g prime of x. Okay. Okay, great. Okay, so you can do multiply by constants, and you can add things and you can subtract things, right? So for instance, and so you can use these rules above, taking the power rule, constant multiple rule, sum rule, and the difference rule. And by doing this, you can take the derivative of any polynomial, right? So let's say we want to take the derivative of 2x squared plus 5x plus 7, right? So we can just do all the rules. So ddx of 2x squared plus 5x plus 7. Well, first we can use the fact that this is a sum to just break this up. This is ddx of 2x squared plus ddx of 5x plus ddx of 7, right? We break this up. And now using the power rule, along with the constant multiple rule, right? The 2 comes down and it's multiplied by this 2, right? So that ends up giving us 4 times x to the 1. And then ddx of 5x, right? That x is x to the 1 comes down and it leads x to the 0. So this gives us 5 times, x to the 0. And then the 7 here is a constant. And the derivative of any constant that we saw, right, is 0. Right, and so if to simplify this just becomes 4x plus 5. Right? What did I want to say? Oh, I forgot. Oh, yeah. Okay. Yeah. So this just becomes 4x plus 5. So, and you can see, you can just do this for any polynomial. You just do every term by itself. If it has some coefficient, fine. You just have to multiply that in. And doing this is much, much easier than actually calculating the limit as h goes to 0 of this whole function applied to x plus h minus that function applied to x divided by h, right? The power rule saves you the trouble of writing down all of these limits and calculating these limits. But you don't have any power rule without limits. Remember, ultimately, anytime you use the power rule, what's really going on underground is you're writing out a binomial expansion and taking a limit as h approaches 0. So that's what makes the power rule work. Okay? It's not true because somebody said it was true. It's true because it's based on a limit. Okay? So this allows us to do the derivative of any polynomial. Okay? we're going to learn more rules over the next couple of weeks about how to do derivatives of things involving trigonometric functions and how to do products and how to do rational functions and all of these kinds of things. But for today, what I wanted to do was just give you rules so that you can do polynomials without having to actually do limits. Okay? And so this is how this procedure works. Okay, any questions on this procedure?
So,
Okay.
yeah,
Yes.
Dad, how are you?
Emmanuel?
This is Emmanuel.
Yep.
Yeah, how are you?
Good. How are you?
I'm already off and on, yeah, because of the network,
Mm-hmm.
but I wanted you to, the concept you were talking about concerning this polynomial,
Mm-hmm.
could you please reiterate that?
Sure.
Could you please? Mhm.
Okay. So let me do this even a little bit more carefully, right? So,
Okay.
well, this is okay. The first step is okay, right? You take a polynomial. What we're saying is we can take the derivative of each term separately and add them together. So let me give as an aside here, how do we do the derivative of 2x squared? Well, from the constant multiple rule, that's going to be the same as 2 times the derivative of x squared. Okay, so this is what the constant multiple rule tells us. It tells us we can pull constants out of the derivative. Okay, so the derivative of 2 times x squared is just 2 times the derivative of x squared. And so what is that? That's 2 times. Now we have the power rule. So the derivative, so going back to the power rule over here, is that if we have the function x to the n for a natural number n, so this includes x squared, then the derivative is given by pulling down the n and replacing it with an n minus 1. So the derivative of x to the n becomes n times x to the n minus 1. So this is true for any number n. So going back to our example over here, the derivative of x squared is going to be, well, we pull down the 2, so we'll get another 2, and then we have to decrease the exponent by 1. So instead of x to the 2, we're going to get x to the 1. Okay, and so now we have 2 times x to the 1, and that is exactly 4x. Okay, so there's really 2 things going on here. There's pulling the constant out and then applying the power rule to x to the n. But after you've done a few practice problems with this, you probably can treat this all as one step. You think of it as bringing down the 2, and that gets multiplied by this 2, and that gives you a 4. And then the exponent goes down by 1. Okay, but what you're really doing is you're combining the constant multiple rule with the power rule. Is that okay?
Yeah. Thank you. Thank you, guys. Okay.
Okay, good. You're welcome. Okay, so maybe the last thing to do before we break is, I don't want to do we'll talk about geometry of derivatives next time. I only want to do the basic geometry. I want to do the derivatives of f of x equals, cx and f of x equals c. So I want to look at 2 types of functions. So this is f of x equals cx, and this is f of x equals c. So we know by the power rule that f prime of x here is just equal to c, right? The power rule says if you have cx, which is cx to the 1, that's going to give you c times 1 times x to the 0, which is just c, right? The derivative, maybe I should say this more specifically, f prime of x is going to be c times 1 times x to the 0, which is just c. Okay. So remember what the derivative means. The derivative is the slope of a tangent line. And if I have f of x equals cx, that's just a line through the origin, right, with slope equals c. And so if I'm at any point along this line, what's the tangent line to a line itself? Well, the tangent line to a line is just the same line, right? the tangent line to a line is just the same line, right? So the tangent line is the same line, and the slope is always C, right? No matter where I am on this line, the tangent line's the same line. It's always going to have slope C. That's why the derivative is just a constant. It's just C, because it's saying no matter what we plug in for x, no matter what our x coordinate is, the slope of the tangent line will always be equal to C. That's what's going on with a straight line here. Okay, slope of the tangent line will always be equal to C. In this situation here, we have that f of x is equal to C. That's just a horizontal line, right? This is, a horizontal line at C. And if I take any point along this horizontal line, well, its slope, the horizontal line, the tangent line is again the same as the horizontal line, right? So tangent line. So here, right, remember we saw f prime of x is equal to 0 if f of x is a constant. Tangent line is a horizontal line. And a horizontal line has slope 0. Right? So slope is always 0. That's not a 0 factorial. That's just a 0 with an exclamation point. And that's why the derivative is 0, because we see that the slope of this tangent line to a horizontal line is, the tangent line just is the same line, and it's always going to be 0. Okay? So that's why the slope of cx, or even cx plus d, if I have a linear function, the derivative is always just the slope of that line. And if that line happens to be horizontal, then the derivative is going to be 0. All right, any questions on this? Okay. Great. Okay, so a few homework exercises. So first one, it's pretty straightforward. So just calculate the derivative of this polynomial. So just to practice with what we did before, let's calculate the derivative of this polynomial here. Second one is calculate the derivative of f of x equals square root of x minus cube root of x. And the hint is, can you write this in a form where you can use the power rule? And then the third question is another one of these thinking questions. It's calculus somehow. You have formulas and computations, but a lot of what calculus is just about ideas, about understanding rate of change, right? So this is a thinking question, which maybe you know the answer to already, some people, but let's not give it away. So the question is, suppose that we have a function that's a product of two functions. So we've already seen the sum rule and the difference rule, right? If h of x is f of x plus g of x, then h prime of x is just f prime of x plus g prime of x. So the question is, if h of x is a product of two functions, do you think that h prime of x is equal to f prime of x times g prime of x? Okay, so that is the derivative of a product the product of the derivatives? And if you're skeptical of this, if you think this is not true, try to find a counterexample where this is false. Okay, try to find a function that is a product of two other functions where the derivative of the first function is not the product of the derivatives of the other two functions. Okay, so if you think that's not true, try to find a counterexample. As always, I'll send this out. I'll send this out to the WhatsApp chat a little bit after class. And so I'll say, so thank you again for your attention. There's no class next week, actually confluence of an American holiday and a Liberian holiday. So we have Thanksgiving and you have Tubman's birthday. So there's going to be no class on the 29th. And then the week after, on December 6th, we're going to do quite a few things. We're going to discuss applications of derivatives to motion in physics. We're going to talk a little bit more about physics. We're going to talk about what it means for functions to be differentiable, what derivatives mean visually. Today was very computational. It was very algebraic. We're going to talk more graphically next time about what derivatives mean. And we'll also talk about higher derivatives. So there's something called a second derivative and a third derivative and so on. So we'll do all of that next time. And by the way, I should say that today, all material was from sections 2.2 and 2.3, and I'll say mostly 2.3. of the textbook. Okay. And so please, if you haven't typed your name in yet, please type it in. And I hope everybody enjoyed the topic today, and I'm looking forward to next time. Yes, Emmanuel?
Yeah. The textbook. What is the name of the textbook? I've already been trying to check.
It's just called Calculus. It's called Single Variable Calculus, and it's by Stewart. Okay. I'll type this into the chat. So Stewart.
Okay.
Single let me actually make sure I have the right title. It's Stewart, and it is called Essential Calculus. Sorry. Stewart, and it is called Single Variable Essential Calculus.
Okay. Maybe form one answer.
I managed to find. I sent it to the chat. I sent a PDF to the chat.
Oh, okay.
I can send another. I can send it again. I've sent it a couple of times to the chat, but the chat gets big and it gets very backed up. So if you look back to the history, I've sent it to you. But if you want, I can just send it again.
Yeah, I beg you, please send it when you are sending the lesson. Yeah.
Okay. I'll resend the textbook. Yeah.
Okay. Thank you.
Right.
Thank you.
You're welcome.
Okay.
Any other questions?
Oh, mine is just a commendation. The presentation was very funny today. You getting me?
A little bit. You went out a little bit.
I said mine is a commendation. Thank you. The presentation was very good today.
Oh, you're welcome. I'm glad you enjoyed it.
Yeah, it was very wonderful. Thank you.
Okay. All right. So you're welcome, everybody. I'm going to stop the recording now. Has everybody put in their name? I think everybody has. Yeah, I think I have record for everybody. Definitely. Okay. Great. Okay. So in that case, I'm going to... Anybody else need to put in their name, or did everybody do it? I want to make sure. Did Uriah do this? I want to make sure Uriah did this. I'm just going to write it to myself to make sure, just because I didn't see it. And okay, I think that should be everybody. And Alexander. I want to make sure that I have all of these names. Okay, everybody else I think has written them. Okay. All right, great. So have an excellent weekend and week, everybody, and happy holiday. And I will speak to you soon. I'll send things out tonight. All right, bye, everyone.